So welcome back. Welcome back. So I had very interesting questions during the break. A few maybe just quickly. One question is, why don't we use a binary search tree? But a binary search tree has only 2 children every time. Here we have many children. Why many? Again, that's for the block access on the disk. We want to try to be efficient by having the leaves the size of a block on disk. Because what typically happens is that the leaves, they will stay on disk in many cases. You keep them on disk and you load the upper part of the tree into memory. That way in memory, you can very quickly figure out what leaves to read, and then you only read the leaves from the disk. Now, you do have some cases in which the index is actually small enough that you load the entire index in memory. That can also happen, then it's just even faster. But it doesn't have to be that the index fits in memory. The leaves could stay on disk, and to read them in block, every leaf corresponds to a block. Okay, now let's see it into action, because the whole point of doing that is to actually have a use for it. So imagine that now we want to build an index on that data. Then we have 2, 3, b plus 3. So we start building 20, 21, got it right this time, 19, and then we split, because in that case, I said that I don't want more than 2 values. That's just because it's very small, so I picked a different parameter. Then we have -4, that's also too big, so we split again. Then we have -6, so here we can decide to merge to just move around the 19 on the right, then we're back to something balanced, and then we add 20 already existed. Now we have the structure. This structure is built once and for all. You have to write down a command on the shell or in a program that is basically what I think I showed you here. Create index century 1. The 1 says it's a b plus 3, a tree index. 1 says ascending. You have ascending century. Hash would be the string hash if you want a hash index, 1 for a tree index. Okay, so you do that. Now that can happen in 2 ways: synchronous or asynchronous. Synchronous means from the moment you press enter after your command, the computer goes all in with the CPU building the index and blocks everything. You cannot use the database anymore until it's done. That's a synchronous build, can take hours if it's a lot of data. And the other way is the asynchronous index build, meaning that it's going to build the index in the background, maybe a bit slower, but you can still continue to use the database. When the index is completed, it can be used. Yes, there is a question? Right behind you.
I hope I didn't miss this point, but my question is, even with hash indices, but also tree indices, what is the issue when, for example, say, maybe this data set is new and maybe the 20th century has a lot of entries, then it means that the leaf node value 20 will have a lot of references, right?
Yeah.
How is that affecting the actual storage? And I suppose the search time then will be affected as well, or?
So indeed, the best indices is when you have unique values. All the values are unique, and you just want point queries. This is kind of the textbook case of an index. Now, indeed, if you have multiple values with that repeats, then you're going to share the pointers. And then, of course, if you have a collection where you have millions of objects sharing the same value, that's actually not good, right? Because then that's very inefficient. But in that case, what you do is just you index on more fields. You can have compound keys, right? Then it's lexicographically sorted. And then you can refine that. So it's probably not a good idea to build an index if you have millions of values that are identical. Yeah.
Essentially talking about maybe data sets where there aren't that many, actually there are less outliers and there are just a lot of values that are.
Oh, you mean if it's imbalanced?
Yes.
Yeah. So if it's imbalanced, then yes, then you would look at the max. Right? What is the maximum size? Yeah, it's both a science and an art, right? When you work on indices, there are people who specialize in that, right? Of trying to build the right indices for your queries, and it's an art. You need to get a feeling for that. But it's also a science, because when you know how indices work and you understand the structures, because you're computer scientists, then I'm pretty sure you understand better what's going on. But I will teach you some of the basics of that. And then the rest is experience, is actually working on collections and building indices and seeing for yourself. Right? Okay, so now This is a range query, but I'm lucky this is not a hash index. If I had a hash index, bad luck, right? But here I have a B3 index. So where's 19? Well, in logarithmic time, I find that it's over there. And then I can go all the way to the right, because what I didn't tell you is that B plus trees also have an extra linked list over the leaves that just accelerates the scanning of the leaves. So from the moment I have 19, I can very efficiently go all the way to the right. Right, very easily. I don't even need to go to the parents for that, because I have this additional linked list structure. All right, and then I return these 4 documents right there, right? Okay, so now what happens is in MongoDB, I told you about this underscore ID, that is the object ID. It's of the type object ID, and it's automatically added to your objects when you import them. So if you import a JSON lines document or JSON into your database, they will get this underscore ID on top of that, based on some obscure algorithm, depending on something on the machine, the time that it is, and blah, blah, blah. So it's creating these object IDs for you. Plus, you have the luxury of having an index on the object IDs, and that's a primary index. It's a tree index. And actually, by default, it's going to shard on that, right? But you can also define secondary indices, hash indices or tree indices, B plus tree indices, and it's really up to you. You, as the user of MongoDB, can decide what indices you're going to build. And if you build them, you can also instruct MongoDB to use this in order to shard your data in intervals, right? Okay, now here are a few more things on indices. Sometimes you are so lucky that you can directly output the results of the query just from the index. Imagine that, for example, the query is just a count of the number of objects that have a specific value. That you can tell just with the index, right? It's just, you just need to think about it. You don't even need to look at the data itself, right? Again, the data is still stored somewhere. The index is in addition to the data. So, so you basically, where was I? That's my train of thought. So sometimes you're lucky that you can use the index. Sometimes you're not. So this is the case where you can use the index. And sometimes you have some additional work to do because the index is not enough. So maybe you want a query that filters on 2 values and only 1 is indexed. So you use the index to pre-filter with the first value, and then you do the extra work in memory with the results coming from your index, right? Then you're faster, but not ultra fast, right? But it's still better than without index, because if you don't have any index, then you have no other choice than scanning through the entire collection. Right? For whom is that clear? With no index, full scan. Okay. With an index, in some average case, you can pre-filter partly with an index and finish in memory. If you're super lucky, you can directly use the index alone without even looking at the data. Okay, so we can create an index that we call hash on name point last. So that's last within an object associated with name, like I explained earlier, like for the queries. Then if we try to query that, name last Einstein, it's going to find in O of 1 the object that has the value Einstein, if there's only 1. But then, of course, you need the entire object. So it's going to read that object from disk where the data is, but it's going to read only that object, as opposed to the full scan if you didn't have the index, right? So here, this is super efficient. We built an index on name last, and we query with a point query on name last. This is O of 1. In fact, you can get that in something like 2 milliseconds. In 2 milliseconds, you have your answer. Super fast, right, on the local machine. For whom is that clear? Okay, you have a question about that?
Hello. Okay. So should we reserve this method only for indices, or can we create can we make multiple columns or like features index, like especially if they are like constantly being used to select documents?
So I'm not sure I fully understood your question. Let me try to answer, then you tell me if that answers your question. First, in the same index, you can specify multiple keys, not for hash indices, but for B plus 3 indices. You can have multiple keys. Second, you can build several indices. You can have 3 indices, 5 indices, 10 indices if you want. Then what happens then at query time, MongoDB is going to come up with strategies and it's going to compute the costs. With a strategy, it's going to use no index. With another one, it's going to use index A. With another one, it's going to use indices B and C. And it just computes the costs and picks the lower costs. And then it executes with that strategy. Right? Did I answer?
Yeah. Thank you very much.
Okay, great. Thank you. Okay, so this is an example where we could use the query, which is very fast in O of 1, and we only need to read that very object from the disk because we know exactly where it is thanks to the index. This is an example where it's not highly filtering. So profession, there's plenty of people with the same profession. We have an index with on the profession. Then we can use the index. So it's going to figure out that a strategy is to use the index, but you have to finish in memory. Because here you want to find profession physicists, but then you're going to have all the physicists. So in memory, you need to only keep those that have relativity in the theories. For whom is that clear? Right. So you're accelerating the query with the index, but you still have extra work to do for the theories part of the query. Right. That's called post-filtering, the keyword for that, post-filtering. Okay, now here's a compound index where you have two fields, birth and death. In that case, both ascending, so ascending birth, ascending death. Then you can query for birth 1887 and death 1946, and that's going to be efficient because you can directly look that up. It's a lexicographical order, and you will find in the index where the birth is this and the death is this, right? You can also say descending if you want the death to be ordered the other way around. So you just do -1, and that's like a descending. Okay. Now, with a 1, that's a tree index. So it supports range queries. So since we have ordered birth in a B tree, then we can look up all the objects where the birth is after 1946. Again, it's not going to be O of 1, it's logarithmic, plus it's an entire interval, but at least you don't have to scan the entire collection, right? This is again what we're comparing with as the base case is the full scan, okay? So with the index, we are only reading the part of the collection that comes after 1946. We don't even touch the rest of the collection. We might also have post-filtering, which is fine as well, right? So we use the birth index for querying some of them, and then we post-filter on the other fields. Okay, now this here is important. It turns out that if you build an index on compound keys, birth and death in that case, but your query only looks for the birth, you can use the index. Why? Because that's actually a range query. Imagine the lexicographic order on birth and death. What are all the births of a specific date? It's an interval. It's an interval between the death in the same year and the death, hopefully as late as possible, maybe 120 years later, right? So this is why birth 1897 is actually a range query on this index. Who understands that? Okay. So you can query on birth and it's going to be able to use the index. Also like this, greater than, that also works with the index. This doesn't work. This doesn't work because here, what's important is that birth is a prefix of the index, but here, death is not, right? Because it's first on birth and then on death. That's what I told you about abusing the order of keys in JSON. We just have to live with that. It's first birth and then death. But here you cannot do that. Why? Because if you look for death 1887, you're going to have to look up for every possible birth because it's all over the place in the index, right? Just because we are not using a prefix of the index. So this would be post-filtering in memory. It's a full scan actually on the entire collection. Okay, so what I'm telling you is if you have a B plus tree on several keys in a specific order, then you get for free an index on the prefixes. So if you have birth, death, and name, then you also have birth, you also have birth dates. You don't actually build these indices, right? These are not indices that you build. It's just that it's as if these indices existed, because with this index right there, you can answer queries on only birth or on birth and death, right? But not on name alone, not on name and death. It really has to be a prefix. Why is that important? Because that's a common mistake. There are plenty of companies that use MongoDB and that build indices. And for example, you have cases in reality of a company that's going to build this index and build this index, really build this and build that index. That is a waste of space. you can just delete that index, and just use that index. This is part of the art of index mastery, to be aware of these things. So you only need to build this index right there, and it's as if you also had these other indices. Who understands that? Right, that's a great way to end the lecture on MongoDB, right? You made it. We check the time. 31. Do we have any questions on MongoDB? Yes, I see 3 hands that are up. You can decide where you throw it. Oh, wow, this is impressive. Go ahead.
So just looking at the filter, I mean, so when you introduced the index on birth and death, when you did a find on that, you showed that there were 2 reads. No, behind a yes. But shouldn't it just be 1 read?
Oh, yes. This is just because what I mean here is that this is all done from this directly. You just directly read. It's a single read. You use the index.
Yeah.
And then it's a single read on this. It's just that the notation I used here was as opposed to post filtering, right? When I put this, then this is handled separately. But yes, maybe I should improve that slide by just putting 1 disk and that's it. Maybe with a line that says it's for both. Yeah. Thanks. Okay, next question over there.
Is it possible to cluster, have clustered indexes, secondary clustered indexes, so your collection is sorted after those instead of the primary keys? Or
Yeah, so it's basically, it goes hand in hand, basically, the way that you shard and partition your data and sort your data. Typically, what's happening is that when you have an index, you can select that index for the sharding on the machines, and then it's going to use that index to order the documents and assign the documents to the machines. What I don't know is whether within a machine you still preserve the order. My intuition is that it doesn't, because that would be inefficient. You would have to always keep the order, and it's on disk, right? So you cannot so easily write to disk. But basically, the partition scheme on the replica set goes hand in hand with one of the indices that is used for the intervals. I'm not sure if I fully answered your question, because that's... Did it answer partly? Okay, awesome. And we had another question right there. We do hops. This is a network course. Before it was a graph theory course with the traveling salesman problem, and now we had a hop. Right, that's applied network theory. Okay, go ahead.
Yeah, I'm wondering if we have the smaller indices. So you said if we have birth and death, we don't need birth. But if we just have birth in an index, is that going to be a bit more efficient than... So querying over birth with an index that just has birth, is that more efficient than querying over birth with an index that has 4 different fields?
Yes, so if you have this index, but you never use name or death, then you're wasting space. Right, then you should use the first index. But again, that also comes back to the question you asked earlier, because it might be that there's very few distinct values, and then the index structure is not efficient. So you have to think about what's going on the machine when you build the indices.
And speed-wise, not just like efficient in terms of memory storage, but like in speed, is the index
in terms of the pointers? Well, I think that you need to think that every time you do a comparison in a logarithmic number of comparisons, so it's more expensive to compare triplets than to compare a single value. Right? Now the question is always, what is the constant of that? Because if it's the bottleneck, then yes, that plays a role. If your bottleneck is reading from disk, then you don't care, right? Because the real constant it's the reading from disk that takes time. So you always have to ask yourself what's the complexity, but also what's the constant? Where is the bottleneck? Yeah.
Okay, thank you.
Yeah, thank you. Yes, you would be right. Yes, it's more elaborate. So you still have the triplets in memory, and you need to extract the value you're comparing. I really don't know the details of the implementation, right? I'm just trying to think out loud. I'm pretty sure you can figure out ways to do it efficiently. So I have the feeling, my intuition, based on my own use in the past of MongoDB, is that it might be faster, but the constant is negligible compared to you know, when you read from this. So I think that you wouldn't have, except in space use, you wouldn't lose a lot by having an index on more keys, right?
Thanks.
But it takes space. Yes. Yeah.
What happens with non-homogeneous types?
How many sites? Oh, sorry, I didn't get you then.
If the type, if birth is not homogeneous, like if it's not only integers, but arrays and objects and stuff.
Oh, yes. So I think it also works the indices. That's because there is this total order across types. So if you have a heterogeneous field, it's going to build the index and just use the order across types. Right? It first sorts by types. You have all the numbers together, then all the strings together, all the arrays together, and so on. Right? Okay. And there was another question over there. Oh yes, let's do Zoom. And
There's
then,
there's one on Zoom. In practice, does the wasted space from indices actually matter? Or I can imagine that the B3 is much smaller in size than the DB itself.
In practice, you do care about the size of your index. That's what experience would tell, because you have to understand that the point of having the indices and being fast is that you can load them partly or fully in memory. Your memory is limited, usually smaller than the size of the disk. So the size of the index actually matters. It also matters because that constrains the number of indices that you can build and have in memory. And when you have a complex use case with a very large collection and plenty of queries with 10 indices, then it starts to be, you know, it's crowded in memory, basically. You can only fit so many indices. So this is why the size of an index actually matters. But did it answer your question on Zoom? I wasn't in front of the screen. Yep, yes, awesome. And then we can go to you, okay?
Yeah, I still have a bit of a confusion when it comes to the sharding, especially with indexes or indices, because I'm thinking in case we have a very big collection. If we have a very big collection.
Very big, yes.
How is that sharding actually done? Assuming, let's say we have 4 machines, so we assume a master and then a worker probably in each of these 2 possible shards. How are they going to be sharded, and then how are the indices going to be stored such that we know on which machine we actually find them and how we query?
Let's go back to the replica sets. So let me give you my understanding. So here, I won't say that I have in-depth knowledge, but on the surface, I can tell you my understanding of what's going on. Okay. Where are the replica? Oh, there you go. I need to go here. Okay. So what's gonna happen, as far as I understand it, is literally that you basically have built one index, a B+3 index on some fields. So you have a total order in that index, right? Then what's gonna happen is that you partition into as many partitions as there are machines. I can't remember for sure if there's more, but it doesn't have to be like in MapReduce or Spark, you want more tasks than slots, right? But in that case, I think if I correctly remember, you split it in intervals such that it matches the number of machines, right? So if you have 3 machines, then you're going to say the first machine is responsible for everything between A and E, if that's strings, for example, then F and P for the second replica set, sorry, not machine, replica set, then Q and Z. What's going to happen then is that everything between A and E is stored on the first replica set. And then the index between A and E is also stored on the first replica set. So the index is also partitioned. It's fully distributed, basically. But you do have this one server that does the glue between the replica sets and, you know, spreads the queries.
The one thing I'm confused about now is I thought that if we assume we have these 3 machines and we have these 3 splits, then you mentioned the machine A, the machine 1 gets the A to E range and so on. Is that also replicated a number of times on the
secondaries? It's replicated within the same replica set. So you have A and E on the machine on the left. So you would have A to E in here, and also A to E here and A to E here, replicated 3 times.
Oh, so that means we actually have 9 machines in total.
Here you have 9 machines, yes.
Yeah, I thought there were 3 machines in total. That's why.
No, this is really 9. You really have this. I think it was a question also. Somebody was wondering the same thing. These are really 9 machines, right? Because again, you are dominated by the disk space. So if you share the machines, you're basically partitioning the disk space, and you don't want to do that. You really want to use the full space on every machine, right?
Thank you.
Okay, and so basically you have the index in here, the index in here, the index in here. So the index is also partitioned. And when you have a point query arriving, then you look up here, you look up here, and you look up here, and then you union the results back to the one entry point to the cluster, right? Awesome. Yes, there is another question. I think it's the last one.
Yeah, what happens when we run out of memory and we add new machines? Do we have to shuffle all the data around and create new indices and everything?
Yes, I think then there is probably some rebalancing mechanism that happens. Yeah.
Okay,
and by the way, the shards are transparent to you. I think you can on the shell query for the shards. You can ask MongoDB how the data is actually sharded. It will give you the intervals. Okay.
One question.
One more question, and then we'll move on to the next lecture.
Just can you use the mics? Sorry, can you use the mic so people on Zoom? Thank you.
Shard 1 there. Is it A to E and then the replicas? Which one is on which? I got confused like in the now from these ones.
So this is the collection. Maybe the slides are confusing. Let me re-explain. So you have a collection from A to Z.
Yeah.
You split it in 3 parts: A to E, F to P, and Q to Z. What happens is that every replica set, I'm confused with my slide, A to E goes here 3 times, here, here, and here.
Okay, yeah, then it's clear.
Then F to P goes here 3 times, and so on. So these 9 machines correspond to these 9 partitions and replicas, right? It's just not drawn in the same way, but this is what it corresponds to.
Yes, thanks.
Awesome. Okay, so let's call it a lecture for MongoDB. That's it. You will have exercises, of course. You can play. By the way, you will find online sandboxes where you can very easily play around with MongoDB for if you just want to play, right? And of course, if you want to actually store data, you need to install it on your machine. You can do it on your laptop, right? It's very easy to install. All right. Thank you very much. I now load the next lecture on querying denormalized data, and I'll be right there in a few seconds.